Hello IB. We're moving on now with the next section on correlation. So I've just started on this page just to remind you of what we were looking at before. This was a case where we had a mass on a spring and the length of the spring was related to the mass that was connected to it. So the mass was our independent variable, the length was dependent, and we can plot the data. We can see the data is all shown here, and we can say that it looks very much like a straight line. So there's a strong correlation to a straight line. It's positive because it's got a positive gradient. But the question is, like, how strong is strong? When do you know to say strong? When do you say moderate? And so this section here looks at putting a mathematical value to that strength. So let's shift this so we can actually see the heading. All right, pop that up there. Maybe that'll work. So Pearson's correlation coefficient is a number that we can calculate, obviously put together by Pearson, that is a measure of that correlation. It's the letter for the correlation is a small r, so it's a more precise way of describing the strength of the linear correlation. So remember, this is always connected with, how does it compare to a straight line? So when we have data that's curved, we'll look at another way of analysing it. And remember, we've got two variables now that we're looking at. You're usually going to be calculating this with your GDC and not manually, but let's look at the formula anyway, just to see where it comes from. So this is the formula. So we might have a certain number of data points. So from our previous example, our X was, in that case, mass, and the Y was the length. So that means we've got a whole lot of different data pairs, N or however many that is. Then what we do is we calculate the average for the mass, the X values, and the average for the Y values, the length, and we do this calculation with it. As I said, you won't have to do this manually in an IB exam situation, but we want you to become familiar, or at least not scared of looking at an equation where we've got all these sigma signs and things being multiplied and squared. So basically what we're doing here is we're getting each X value and subtracting the mean to see like the difference, how far away it is from the mean, multiplied by the difference between the Y value and the average, or the length. We do the same for the denominator, but now we square it, then we add them up. So same story here, we're going to square it and then add them up. And then once we've added all those up, we then do the square root. So that's the process. So when we do that, we find we come out with R values that are between 1 and -1. So our R value is less than or equal to +1 and greater than or equal to -1. And what we find that is that for the direction, when we have R values greater than 0, in other words, they're positive, it's related to data that's, say, in a positive trend. That's what our data would look like. If our R value is less than 0, so it's negative, we find that occurs when our data values have a negative pattern. So it's not talking about how strong it is, it just says there's a negative correlation between them. So the R value tells us about whether it's increasing or decreasing. The strength, that's related to the absolute value of R. Remember that symbols, the straight lines is the modulus or absolute value. So if that equals 1, then we've got a perfect correlation. All right, and the smaller the number, the weaker the correlation. So that's ignoring the plus and minus. So the smaller the absolute value of R is, the weaker the correlation. All right, so here's a table of what data could look like, and we've seen here when r is equal to +1. All right, that's our perfect correlation. It's positive. So it means all our data is going upwards. As x increases, the y increases. There's a positive correlation, and all the points lie exactly on a straight line. It's a perfect positive correlation. A perfect negative correlation, so these are the negative ones, means they lie on a straight line, but now it's negative. As x increases, y decreases. So we can see now as our value gets slightly less, the data starts to spread around. Here we've got 0.87 to 0.95. It's more spread. So we talk about a strong positive correlation. So always those two parts, strong, the strength of it, positive, the direction. Here we're now down at 0.5 to 0.87, so the data's even more spread. It's moderate correlation, and our weakest correlation is starting to be spread all over the place. No correlation means we can hardly tell whether it's increasing or decreasing as x increases. So the spread of the data, how broadly it's spread, is the strength, and the value of r will tell us that. So let's do one calculation just so we can practice using that formula and be familiar with the sigma notation. So here we've got some fertilizer that we're looking at and the amount that the lawn is growing each day. So the fertilizer is measured in grams. That's one of our variables. The lawn growth in millimetres is our other variable. So I'll put the data into the table. So given this is our rule down here that we're heading towards, that's what we want to work out. That was meant to be a star. Didn't quite look like it. So let's just get rid of it. Okay, so what we want to do now is to do x minus x bar, the mean. So to get the mean, we actually just have to calculate that out. So if we add up these scores, we've got 5, 10, 12. 4 scores, so sigma means sum of. So if we've got 4 scores, then our mean is 3. Y bar, we've got 8, 6, 14, and 6 is 20. So our y, the average of the y's is 5. So now what we do is we subtract these. So we're going 1 minus 3 is minus 2. 2 minus 3 is minus 1. 4 minus 3 is plus 1, and 5 minus 3 will be 2. All right, so we then work out the y values. So we're going to go 3 minus 5 is minus 2. All right, 3 minus 5 is minus 2 again. All right, I'll let you fill in the rest. We then say, let's now multiply this value by that. So we want minus 2 times minus 2 makes plus 4. Minus 1 times minus 2 makes plus 2. We also need x minus x bar all squared. So we want this value all squared. Minus 2 times minus 2 is plus 4. And this is going to move out of our road down here. We now want to square this one. That comes out as 4 as well. And this one squared becomes 1. This one squared becomes 4. So pause the video, fill in the other squares, and fill in these totals, because we're going to need these totals for down here. Okay, hopefully you've filled that in now. So now we can put all these into our table. So to get our R value, or into our formula, to get the numerator, we need the sum of those two multiplied. So that was 13, divided by the square root of the sum of the x minus x squareds, which was 10, times, and that one's 18. Pop that into your calculator. Okay, so putting that in your calculator, you've come up with this value. and obviously we can round that to 3 significant figures, which comes to 0.969 to 3 significant figures. And if we look back at our table here, we saw that 0.969 comes in as a very strong correlation. Not a perfect correlation, but very strong, which means the points are very close to a straight line. Now, all of this you can do with your calculators. So here we're going to be setting up this data onto a data spreadsheet. And then remember, we're going to be analysing the data with 2 variables. And we'll come out, when you do that analysis, you come out with an R value, where we're getting the correlation of the R value shown down here. That's R squared, there's our R value. So we're looking at the R value. This one here, the R squared value, we won't be looking at. So I'll do another video later with showing you exactly what to do with your calculators, or else we'll do it in class. But as I said, all of these we'll be doing with your calculators rather than manually. So thanks for listening, and we'll catch up with you later. Bye for now.